Hi everyone, thanks for inviting me to this talk to talk about Findsight, which is a project I recently launched. So who am I? Hi, I'm Pierre, aka Turbo. I'm not a developer, so it feels kind of weird to talk to a development organization, but I'm actually a product manager for CodeQL, which is the analysis engine that we develop at GitHub for code analysis for security. And I'm not the only product manager for CodeQL, but I kind of manage the overall strategy, our language support for dynamic languages like Ruby, JavaScript, Python, but also C++ and Swift, and the experiences and foundations teams that are delivering our great capabilities to our customers. But I still moonlight as a developer, right? You can't beat that out of me. My background is development. I worked at SolarWinds previously and a few startups before that, from everything from like code analysis to networking software and general purpose compute on GPUs, which is how I got my Turbo handle from Turbo.js many years ago. Why did I do this project? Well, I like learning by doing. And if I'm expected to kind of productize our AI capabilities, I want to have some idea of what it takes to go from an idea of using these large language models and AI to a final product that users are actually, well, using. And selfishly, I also wanted to learn more NIM. NIM is a fantastic programming language. I think everyone should be writing NIM, but you'll see some symptoms of NIM's greatness throughout this talk. Today, you'll learn something, hopefully, maybe I convey some information to you, namely, first of all, what Findsight even is, because I haven't told you yet, why NIM is amazing, again, and a bit about how to work with large language models, a tiny bit about how to prompt them, but we're going to learn more about embeddings, which are the way we find similar pieces of text, which is what Findsight is all about. And we're also going to learn how to build a hybrid search engine from scratch. And at the end, I promise, once we get through all that theory, there's a bit of fun when we take a look at what users have been entering into Findsight as a query for which they want to find recommendations for, because people have some really weird ideas of what they want to learn about. But enough talking, let's have a demo. Right? Let me just show you what Findsight is. So you can use it, it's public, it's free on findsight.ai. And the best way of explaining what it does is just to start out with a random search. What this will do is Findsight will pick out what is called a claim for us up here. And what Findsight does is it analyzes books, articles, websites, papers, and it extracts the core claims, like the core statements these sources put forward, and then it indexes them for you to search through. And in this case, it has picked out a claim about Fairchild Semiconductor that was founded in Palo Alto, etc. And it has picked that as our origin. And from that claim, it finds sources that talk about this sort of topic. For example, this particular claim comes from the book by this person called Making Silicon Valley. And there's another related book by Arnold T. about Moore's Law. And you can see there's a different angle on that same data point in here. And this is a really quick way to find sources that talk about the same sort of topic or concept or tackle an issue from different perspectives. But the real power comes in once you go from there and start exploring. So if you click into one of these books, for example, we can see there's now more context, right? Further claims are displayed to us. And we can pick any of them as an origin, for example, this one about Bell Laboratories, and we can click this explore arrow and use that claim as an origin, and then read more about Bell Labs and how sources are talking about that institution. So that's pretty cool. But the real power of Findsight comes in through the powerful search engine that allows you to, instead of starting at a random place, start at a place you actually want. So we've already seen what that state filter does, right? You can read this from top to bottom basically as we're going to find sources that state this claim, but we can also just use normal text search through the mention filter. Let's say we want to search for running, right? And we find sources that are related to running lean, your brain on sports. Oh, but there's also this one in here, which is an article by this educational institution, and it talks about run-prone private debt. I don't actually know what that is, but it's definitely not related to running the sport. So text search is pretty error-prone that way. One step beyond text search is the knowledge graph that Findsight builds. And you see some of the extraction that we're doing around knowledge by the tags that are listed below, beneath each source title. For example, this one here is about running lean as in a business. There's a business plan. It's about pricing. It's about product market fit, etc. And we can use these entities or tags to explore sources that talk about a particular concept rather than just a particular piece of text. So instead, if we want to, say, find sources that reference certain concepts, we can enter the same thing in here and find suggestions. So we have running as a skill. That's a named entity, right? It's just a string that has a category. We find running with a little Wikipedia icon next to it. That's a linked entity that links to, unsurprisingly, Wikipedia. And we can just add a few of these, for example, 5K run, sure, sprinting, and then we can search for that, and our results will be constrained to sources that talk about running as in the sport activity. But where does AI come in? Well, you already saw a bit of that via the state filter, but something really powerful about large language models is they can be used to answer questions. But there's a risk associated with that, right? Because as you're probably aware, when you ask ChatGPT something, for example, it can just make up stuff. What it outputs might be plausible or might look convincing, but there's really no way for you to check if that's true. Now, Findsight uses large language models like GPT internally to find claims that answer your question without the risk of that hallucination. So if we try that, for example, let's use this answer filter and say, I don't know, what's the average temperature increase from climate change? Then it will underneath use GPT to index our existing knowledge base and come up with claims that answer it. For example, we get global warming is a reality and there's a temperature increase of 3.5 degrees Fahrenheit by 2100 years. And instead of that text being related to what we've entered, it actually answers that question. So that's Findsight in a nutshell. There's a lot more you can do with these filters and combining multiple of them all together, but that's the core value Findsight delivers. Now let's talk about how this actually works. What goes into building something like this? What goes into working with these large language models to have knowledge extraction that is reliable, and how do we actually search through this knowledge? This is a long theory section, but I promise at the end we're going to take a look at something fun. So stick with me. We're going to talk about this in two parts. The first part is the indexing, so how we acquire content and put it into our knowledge base. And the second part, the more interesting part, is the searching aspect. How can we combine entity search, full text search, and AI search together into one cohesive search experience? So let's get started with this indexing pipeline. The first step is to acquire content. And this content comes from many sources, right? Maybe PDFs stored in a web archive, or blogs or news articles posted to websites, or books that are present in some sort of ebook format. And what the crawler does, it generates this format right here. Plain text paragraphs with basic support for unordered and ordered lists, right? We have a few paragraphs and an unordered list down here. That's it. References, footnotes, formulas, tables, images, figures, all that is removed, and we end up with this clean text. There's a lot happening under the hood here, but that's the simplified view into it. And now the next step, of course, is to take that text and put it in front of a large language model and ask it to extract those claims. But that's deceptively simple, because a large language model has one interface, and that's a big text box, essentially, called its context window. And within that context window, we have to fit all of these blocks. We have to fit the original content that we want to extract. We have to fit our instructions for the extraction, and we have to fit the output. In this case, for example, the topic and claim extraction happens in one shot with a large language model in Findsight. And adaptive chunking is the kind of algorithm that you need to design that's very data dependent to make sure you put the right amount of content in here in the right format. Because there are many pitfalls with this. For example, if you have too little context in here, say we just take this one sentence, right? let's consider the input would just be this one sentence. And we ask a large language model to summarize it in like 5 bullet points. Then we get back 5 bullet points because the model will always obey your instructions. The problem is that goes far beyond the content that would be in that one sentence. And it would start to hallucinate. It would start to make stuff up that sounds plausible. Now for Findsight, that isn't such a big problem because most of the content that we deal with is already part of the training set for GPT. So it knows, quote unquote, about that text, but it's still something we want to minimize. We want it to stick to this content. Or consider what happens when you are in a list item, right? If you have a bullet point list in the text or any sort of text, the preceding paragraph usually isn't the end of the paragraph before it, but it's actually an introduction to the list after it. So if we encounter a list, we have to backtrack, we have to send off the previous chunk, then consume the list and send that off. And all of this together falls under the umbrella of adaptive chunking. But there's yet another problem which is unique to large language models. Let's take a look at an example of 3 claims it has extracted that were caught by a filter. The first one is fairly normal, right? It says falsehoods can range from false statements by people who think they're true to lies by people who know they're lying. Fantastic. Perfect claim, perfect length, and it's actually what's in the source. The second one is a bit weird. An exercise to help start stripping away false narratives and limiting attributes is to list general topics in the form of hashtags. That's not something that was in the original source. It doesn't talk about hashtags or listing topics or stripping away false narratives. This is what's called a prompt leak. That's another side effect of the interface to large language models just being a text box. It doesn't know where the original text ends and your instructions begin, at least not as of now with the models that we have. So sometimes it will just read past it. And in this case, it has decided to weave the instruction itself creatively into the text and pretend the author of the original text has said this. And this is really hard to catch. In other software, this is much more of a problem. If you recall, when Bing Chat first launched, the prompt was leaked within like hours. It's not secret information, but it's kind of the last minute instruction to how the model should behave. And in Findsight's case, it's just weird to read this. Like the risk for us is we pretend that an author has said something when they haven't, and we need to filter this out. How do we do this? Well, we do this through supervision by another machine learning model. So we embed, and don't worry if you don't know what that means. Basically, we just generate a fingerprint for the prompt, for the instruction, and for the output. And if they are too similar, the chunk length is adapted until that anomaly goes away. And if it can't adapt it, so it does go away, then it's flagged for manual triage. So just something to pay attention to if you're instructing a model to do any sort of task, including summarization and extraction. Much of Findsight is based around embeddings, and embeddings are a way to turn a piece of text. In this particular case, embeddings are a more general mechanism, but in this particular case, embeddings turn a piece of text into a vector. And in OpenAI's case, these vectors are huge. There are 16-bit floating point numbers, and there are 1,536 of them for any text that you embed. You can embed short text like single phrases or really long text like the entire content of a source. But for Findsight's case, the most common embedding that is used is the claim level embedding. And the general assumption is the more similar, by some sort of metric, these vectors are to each other, the more similar the original text is to each other. And that's how we find similar claims. And we're going to talk all about how that works in detail later. Then there's another machine learning model in the mix. So we're going away from GPT and we're now talking to Azure CS, and particularly their LER and NER model. LER stands for linked entity recognition and NER is named entity recognition. And we already learned what those are. Those Wikipedia entities are linked entities, and the named entities are just strings that we can assign categories to, right? But we're also building a full text search index because we need to both let people search with full text queries, but we also need to let them search for suggestions of entities. So for example, here you can see some of the advanced syntax that is supported by this full text search, like prefix queries or alternatives. In this case, we find both running and Washington with this one full text query. And the last and most infuriating part of this is metadata acquisition. and data cleaning. When you're preparing training data, 20% is data acquisition and 80% is data cleaning. Here's an example. This is data we get from the publisher's ISBN catalogs. So for books, for the date field, year published. And on the left are the values we get from publishers. On the right are the values you would expect. I didn't know what this was. This is apparently decimal days since 1991, which is how Excel stores dates. And you can see how data entry goes wrong. So you have to do all of that data cleaning and normalization before you can consistently derive insights and search through the data. But that's it. At the end of this pipeline, we have extracted and embedded everything left, right, and center. We've built graphs. Everything is now present and all goes into one single file. And some of you might now facepalm and say, this is a terrible idea, but everything goes into one SQLite database. And actually, according to some back of the envelope calculations, Findsight could scale to 100 to 1,000 times more content without running into any performance problems. So SQLite is not a bottleneck, and it actually gives us several advantages, but we're going to skip over that because we have a limited amount of time today. But basically, everything goes into this one database and everything gets served from there as well. And now we'll talk about the second part, actually searching. And the next diagram looks intimidating, but I hope I can make this easy for you. Basically, the filters that we offer users fall into 3 different categories. And those categories are the alpha filters, the beta filters, and the gamma filters. Alpha filters are graph queries. So we have this knowledge graph of entities, right? One entity like runner might appear in many different claims and many different sources. And we have topics as well, which are assigned to a source. And we just query whether or not a claim or a topic contains this entity with a given confidence, right? We query this graph. The beta stage concerns anything that is full text search. So the mentioned filter we looked at before, but also the entity suggestion queries as well. And the gamma one is the most interesting one that we're going to talk about. This is the kind of machine learning embedding retrieval stage where we find similar embeddings by issuing a KNN or K nearest neighbor search across the index of embeddings that we have. But Findsight's unique kind of architecture allows all of that to be merged together in one final step. Out of this graph query, we basically get a number of occurrences and confidence values for entities. Out of this beta stage, we get BM25. Don't worry about what that is. It's frequency ranking for full text search, but it's a different type of ranking. And out of the gamma stage, we get yet another different type of ranking, which is similarity as a real value. And in the end, we need to boost these differently, resolve conflicts, and merge them together to eventually render the list of results you see for your search query. So that's the kind of more complicated part. But let's break it down into the individual stages. And throughout all of this, keep in mind that one or all of these stages may exist, right? You may only have an alpha query in your search, you may only have a beta query or a gamma query, or all of them. And we want these stages to optimize each other. So if there's an alpha stage that restricts the kind of amount of sources that we have to look into for matching claims in a beta stage, we want the beta stage to ignore everything outside of that. So that's what these push down arrows are for, right? The alpha stage, if it exists, filters the beta stage, that filters the gamma stage. And so we kind of run the least amount of queries and iterate over the least amount of data for every query possible. Let's take a look at the alpha stage very quickly. So this is a simple set match, right? There is an entity. That entity matches with some sort of confidence to a claim. Imagine a graph, right? You have a node that's the claim and a node that's the entity, and they're connected by an edge, and that edge has a weight that's the confidence. And for linked entities, there's another edge to Wikipedia where the actual normalized definition of that term lives. But this is deceptively simple because even within this stage, we need to do conflict resolution and boosting. What if there is a named entity and a linked entity match at the same position? What do we boost? You can have multiple filters. How can we combine them to kind of optimize the queries that we run against the database. And there is also a kind of variable conjunction. So you might have missed this before, but when we added entities to our pool here, we had this new drop down where we could choose if a source has to match any of them or any one of them or all of them together. So we also have to take that into account and merge them all together. So kind of deceptively simple, but the simplest one of the stages to implement, right? We just need to query this simplified graph. The beta stage is interesting. So if you've worked with SQLite before, you're familiar with FTS5. FTS5 is basically that syntax that I showed before with those prefixes and the alternatives and whatever that you can enter to find textual documents within a database. But there's a problem with FTS5. It's really powerful and it's nice, but it's extremely weird and it's very counterintuitive to use. For example, here's a query. This query has two tokens, foo and bar, and for a document to match, it has to contain both foo and bar, right? The more tokens you add, the more narrow your search will get. Because there's a rule in FTS5 that you get an implicit and inserted whenever there's a separator. Remember that rule. And so this is a valid query. It finds documents that contain both foo and bar. What about this? Well, this is a prefix query. So we still have to match bar, but we also now match documents that contain tokens that start with FO and then continue from there. So football or, I don't know, foosball, I can't think of any other words, would all match this token as well. What about this? This has stumped me for a long time until I actually read the documentation 5 times in a row. I would have expected this query to produce documents that don't contain the token foo. But actually, this is a syntax error. Because unlike in any other language in FTS5, not isn't a unary negation operator, it's a binary set operator. In your head, if you think of not as except, which is what this operator is called in SQL, you'll see why this is a syntax error, right? We can write this foo not bar, and we'll find documents that contain foo minus the set of documents that would contain bar, but there's no unary negation. So already pretty weird. What about this? So since we have operators like not and or and, there's of course a way for us to indicate precedence by grouping things into parentheses. And that's completely valid, right? Parentheses bar is a valid token, parentheses foo is a valid, just foo is a valid token. This is a syntax error because it turns out that the implicit and rule for some reason doesn't apply to queries that contain a group on one side. So very counterintuitive. This one is valid because we have an explicit operator next to the group. And then there are also functions for some reason in this query language, which I think is a massive design mistake. This is a sparse query, right? This finds documents that have the token foo and bar in that order with at most 2 other tokens in between them. That's completely insane. That should be a function that's in the SQL language and not within the actual text syntax. And there's more stuff like column filters and everything else. So it's very confusing to users. We can't relay that to users directly, but it's also a risk because if you think about parentheses and alternatives and prefixes, it becomes very easy to construct a pathological query that will knock down your server because each one of these alternatives is now executed independently and takes seconds to complete depending on your data. So even if we limit the length of search queries that users can post, we still have a big problem here. So what's the solution? Well, the proper solution would be for SQLite to offer you to set limits for complexity, for example, but that's not a thing right now. So what can we do? Well, we can invent a new language, which I'm going to call SafeTS5, which is a subset of FTS5. And here we can observe some of the strengths of the NIM programming language. We can just write a grammar. In this case, this is a parsing expression grammar. And we can mix that freely with our NIM code. So for example, we have a grammar rule here that says expect end. So we expect the inverse of 1, which means any character. And if that's the end of the string. And if that doesn't occur, then we match unexpected. And in the unexpected rule, we just have this code block, just NIM code written inside of our grammar. And that will execute and capture the illegal character that we just encountered. And the nice thing about this is at compile time, this actually outputs a diagram of your grammar. You get this nice railroad diagram, which is really nice for debugging a grammar that you wrote. And it's also compiled into basically a big case statement. And if you don't know, NIM compiles to C code. So this will be optimized by the compiler as well, and is extremely fast, much faster than makes sense to measure. And once deployed, it looks a bit like this, right? We can now enforce minimum constant lengths for tokens. We can now limit the complexity of queries, and we can now also have illegal characters that we don't want in our queries. So we are protected now from the kind of DOS or denial of service type query that people could previously enter into this field. Let's talk about the actually most exciting stage here, the KNN search engine. How do we find similar embeddings or similar claims? Well, we need to start by converting those claims into vectors, and then we want to work with those vectors. So for a statement, like a claim you can make, it's pretty simple, right? We take a claim and we embed it, and then we get a vector out of it. But what about that question that I showed earlier in the demo? What if we have a question? If we embed this question, what we're going to get is text that looks similar to this question, but not actually answers. So what we're doing instead is we're employing a technique called hypothetical embeddings or hypothetical document embeddings. We're asking a large language model, in this case GPT, to come up with 3 hypothetical answers to this question. And remember that you can't trust the output of large language models unless they have access to like an API or a search engine, right? They could make stuff up. But the point is the output looks plausible. It uses all the right words, it's the right length, and it's an answer and not a question. So we can embed these, throw this text away. We don't show that to the user, but we can embed these, average all of them, and then we have our query vector. Now we want to find similar vectors in our database to this query vector. How are we going to do this? Well, there's a naive approach. We can just check every single vector in our database, right? We have our query vector here on the left. And remember, these are 1600 dimensional vectors. And on the right, we have our pool, which is basically the embeddings of the claims in the database. And Findsight has nearly 1 million claims that have been extracted from different sources. So this is quite a large set of vectors in the index. And we compare them. And it's not really important what that comparison function is. It's a cosine similarity. The vectors are normalized, so they fall in the unit sphere. And on the unit sphere, the cosine similarity is just the dot product, which means that in the end, we just have to calculate the dot product between the query vector and each one of these vectors. And then we keep a min heap or binary queue around with an invariant that says that the lowest index has the least similarity. So you can see an example here. Here we have index 2 that refers to the pool with similarity negative 0.2. And then the last item here is the least similar one with a lower similarity score. And the invariant in the min heap only applies to that last index, not to the entire list. We do that comparison, and at the end of it, we drain this heap in order, and we get an ordered set of the k nearest neighbors. So what does this look like if we were to implement this naive approach? A bit like this. We have an outer loop where we iterate through the entire pool of vectors. We have an accumulator for our dot product, which is a floating point number. We have an inner loop. Remember that this inner loop happens 1600 times because our vectors are 1600 dimensional. And we do a multiplication, and then we accumulate into an accumulator, and we offer it up to the min heap. If it wants it, it can fast swap it in, perform resifting, and then we have our invariant again. But there's a problem here. These are floating point multiplication and floating point additions, and CPUs don't like floating point numbers whatsoever. But what do CPUs like? Well, they like bits and bytes, right? So how can we go from these really dense and high dimensional floating point vectors into something that we can represent in bits and bytes? Hopefully in a bit vector that we can pack into some sort of number our CPU can work with. Well, we're going to apply an optimization that is really old, called random projection. That's been around for a decade or more, and particularly an optimization called superbit. And by all accounts, this shouldn't work. If you try this optimization on uniformly random data, you get terrible performance. This is basically a way for us to approximate the similarity function over a binary vector by not using the floating point vector. But the problem is it doesn't work very well. But for some reason, and I don't think anyone really knows why, but for some reason, the embeddings from OpenAI and from other large language models that are even higher dimensional lend themselves extremely well to this type of optimization. So we want bits. How do we get bits? Well, let's imagine a very simple case. We just have two-dimensional vectors, and we can visualize them as a point. But we don't only have one vector, we have multiple vectors. How do we get one bit of information for each of these vectors that gives us some bit of information about their location, or basically their direction? Well, we can draw an arbitrary line that divides this space. And now we can assign a high bit to everything that's on one side of the line and a low bit to everything that's on the other side of the line. And since we're working in real systems with limited floating point precision, there might be a case where it falls on the line. We just quantize that into one of the spaces as well. And we get one bit of information. We can now definitely say this vector is either on this side of the line or on this side of the line. But that's not very helpful, right? We have a huge amount of information loss from just that one bit. So we keep drawing more and more and more lines. And the amount of lines we draw is called the code length. And in the case of Findsight, the code length is about 10,000, which means we draw 10,000 of these lines, we get 10,000 bits of information. And this bit vector is what we're going to work with in the end. Now, in 1600 dimensional space, this looks a bit different, right? If you imagine this in 3-dimensional space, the line becomes a plane that divides the space. And in hyperdimensional space, we are calling this a hyperplane. And we're generating 10,000 random hyperplanes. And then there's another optimization, which is not important within Superbit, that orders these planes in a particular way that increases precision. But the point is we get 10,000 bits out of it at the end. And on our platform, we can take the biggest uint we can get, which is probably 64-bit, and we can pack 10,000 bits into 157 of those uints. So this is okay. It makes intuitive sense that we retain some amount of information from doing this kind of left-right decision-making on each of these hyperplanes. But why does the similarity of bit vectors translate to the similarity of floating point vectors? Well, that's the underlying assumption between the superbit optimization. But we have to change our similarity function. Previously, we used the cosine similarity over unit vectors. For bit vectors, the way we compare them is through the Hamming distance. And so our inner operation now becomes much simpler. Instead of doing a floating point multiplication and a floating point addition, we now just have to XOR the component scalar at a position in the query vector and the pool vector. And we get a high bit for the bits that are different in that component. That's the Hamming distance. Then we just need to invert that to get the Hamming similarity. And then we need to do a pop count, which is a CPU instruction to count the number of set bits within an integer. And we accumulate that into an accumulator, but that accumulator is also an integer. So this becomes an integer addition and not a floating point addition. So we went from really expensive, no good floating point number calculations to 3 CPU instructions for this inner loop. But we don't stop there. We can also now, since we're only working with 157 components instead of 1600 components, unroll this loop. On a NIM, we can do this with a static for. So we basically end up at compile time with 160 lines of code. And these instructions are small enough that all of that inner loop can fit into the instruction cache in the CPU. And we get a bit more performance than if we were to do this in a loop. And just remember that we're doing 10 times less work. So no longer 1,600 iterations, but 160 iterations now. And we also need to apply the pushdown filter that I talked about earlier, right? We don't have to do this work for vectors that we know we don't want to touch. So we look into our pushdown filter and say, Should we be comparing this vector? If not, we just skip over this entirely. And then we can parallelize it, which is really fun. And this is where NIM shines again. NIM has access to a library called Weave. And if you've worked in C++ or C#, you might be familiar with OpenMP or threading building blocks or TPL data flow or any sort of other data parallel thread scheduler library. Weave is faster than all of them. It's based on completely new research about message passing between worker threads, and it enables us to schedule work like this. And by work like this, I mean a handful of CPU instructions across our cores and threads in our CPU with near zero overhead. This scales almost linearly. And it's really convenient as well. We just need a sync scope, which basically says everything within here can happen in parallel, but at the end of this scope down here, wait for this to complete. Our for loop becomes a parallel for loop, and we just need to inform Weave what kind of data we want to pass between the worker threads as well. In this case, for performance reasons, we're just passing pointers, since this is immutable data, except for our output accumulator. So how fast is that? Like, we've talked a lot about performance optimization, but what does it actually give us? Well, let's consider 1600 dimensions, slightly larger than the vectors we get from OpenAI. Let's start with a case of just 1000 vectors. And I'm also putting the number of dimensions here because it's kind of counterintuitive just how fast that number scales. So at 1000 vectors, we're already at 1.6 million inner loop operations, right? And of course, this is very fast, but this is more an exercise to measure the overhead of our solution. So for BF, which is the brute force approach that I showed earlier, going over 1000 vectors takes about 1.4 milliseconds on average, right? In parallel, we can do it in about 300 milliseconds. But if we take a look at our superbit optimized version, we're taking, well, 55 microseconds. That's pretty good. And we're also seeing that that goes up again for the parallel version. That's because the benchmarking solution I'm using here has to stand up and tear down multiple threads. So that's basically the overhead of the benchmark. But what if we actually use a bit more realistic data and go to 5 million vectors, which are 8 billion dimensions? Well, then the story changes slightly, right? Our brute force solution is no longer viable. It takes 7 seconds to complete. But if we go all the way down, our superbit optimized and parallelized version now takes 42 milliseconds. That's 120,000 signature comparisons per millisecond. That's pretty good. The gold standard here is about 50 milliseconds. So if you were to, say, deploy another vector database like ReadySearch in Redis or Weave V8 or Pinecone or something like that, you would aim for about 50 milliseconds over your entire data set. And just as a point of comparison, I tried to price this out in VV8, which is a commercial vector database. No relation to Weave, by the way, that's just a weird coincidence. And the cheapest price you have to pay to just store 5 million vectors or 8 billion dimensions is about $400 a month, with no high availability and much higher latency. So pretty good that we can do this with just this local optimization. But there are more optimizations, right? How do we get from this 10 billion dimensions to 100 billion or a trillion dimensions stored? Well, I'm just going to tell you what they are, and I encourage you to read about them in your own time. The first one is kind of cheating. We can make better use of the hardware we have. We need to make sure that our inner loop is actually vectorized if we're still working with the floating point vector. But we can also schedule the work on better hardware coprocessors. So for example, in Apple Silicon, we have a secret instruction set called AMX for vector processing on the CPU. We also have the dedicated Apple Neural Engine to do vector arithmetic on dedicated cores. And of course, we can schedule all of this on the GPU. The most amount of gains that we can get here is actually the signing step, right? Where we take that collection of hyperplanes and we come up with that bit vector. That's something we can do on a GPU or on an NPU and get a massive speed up. But really, that's cheating. Like, this is not an algorithmic optimization. Is there another thing that we can do? Well, if you think about it, what we've done is we made the inner loop of our comparison operator approximate, right? We went from an exact floating point precision notwithstanding, exact cosine similarity calculation to an approximation of that similarity via bit vectors in the Hamming similarity. But can we do something similar to our index? Because we still have to go through every single vector in our index. And it turns out, yes. That's a very complicated data structure called HNSW. To briefly touch on what this is, basically we're building graphs instead of building just a flat list of vectors in our pool. So let's take this middle bit here, for example. Each of these nodes is a vector, and vectors are connected to similar vectors by edges. The amount of vectors they're connected is called the friend list. And these graphs are small world graphs. That's what the SW stands for. And we tune the amount of connections we make to make it possible for an algorithm to efficiently traverse this graph, which is we make it navigable, which is what the N stands for. And then we put it into kind of a three-dimensional version of a probability skip list. And that's what this kind of hierarchy of sheets is for. So if we enter it at the top, we get to the most similar vector into a local minimum. Once we reach the local minimum, we drop down in the skip list into a denser representation of the graph. We do that again, we drop down until we find the nearest neighbor to our query vector. And all those teal nodes we can skip, right? We're touching less vectors for our comparison at any given layer. Now, there's no free lunch. Constructing this data structure is extremely expensive, and it can't all be parallelized. So there's a parameter tuning you have to do that gives you a trade-off between memory consumption at search time and at index build time, as well as performance and recall, which is basically how close is the approximation to the exact calculation in the end. But for Findsight, that isn't a problem because we can take all the time we need in the index construction, right? If it takes many seconds to index and extract a book, that's fine. We can do that in parallel. But we want to optimize for search performance. So that's a good data structure. If you want to learn more about that, I encourage you to read this free textbook called Facebook AI Similarity Search, the Missing Manual, put out by Pinecone, which is another commercial vector database. It will teach you all about HNSW and other stuff we haven't talked about, like product quantization and IVF indexing and so on and so forth. But those are the major optimizations in here. Now, you have made it to the end of the theory section. I'm proud of you, and thanks for sticking with me. Now, is anyone actually using this, right? We've optimized this left, right, and center. We spent months collecting this data, and 8,000 lines of NIM code later, is anyone actually using it? Well, the answer is sort of. So it's been out for about a week, and in that week, we went just above 2,000 users. Not great, not terrible, but those 2,000 users are enough users to enter some really weird stuff into Findsight, because it's essentially a text box on the internet and it doesn't require a login, and people will enter really weird stuff into text boxes on the internet. And I have put a kind of random selection of the things that I found interesting here. You can see that people want to learn about everything, like find citations for lots of AI topics. From AI is bad to good to will take over the world and doom us all, and other things like the Earth is a pyramid, which is a new one I hadn't heard before. But I'll leave that slide up, and we reach the end of the talk. If you have any questions, feel free to put them into the link or ask aloud, unmute yourself, and we can get to those now.